Hello everyone, I Raghav Arora along with my colleagues Aryan Babar and Shubham Barve of Sardar Patel Institute of Technology are going to present our project for the subject of signals and system, which is based on metal detector. Our faculty mentors for this project are Professor Najib Gatte and Professor Shanti Swami. So let's begin. Introducing a project, it's basically showing how metal objects are detected. It also uses a CRO, which basically is used to detect a few items. Then the main principle on which this project works is called amplitude modulation. It's basically when a metal object is placed inside the detecting coil, then some of the flux passes into the object, and that's why it creates a current called as eddy current. But as we know, it shows a real behavior, and that's why some of the magnetic flux is used up, and hence less flux is available for the next coil to be received. And that's why the coil has a lower output compared to the first one, which causes the second transistor in the circuit to be turned off slightly, and hence the voltage on the collector rises. And consequently, this allows the third and fourth transistors to oscillate, which pass on a signal to the fifth transistor, which drives the mini speaker. So coming now to the components used. First are the resistors. So we have used 0.25 watt resistors. There are various resistors here, so there are various values to it. Then comes our mini potential meter. It is basically one 500 ohm resistance mini potentiometer, which is used to vary the resistance. Then we have used a ceramic capacitor, two ceramic capacitors actually of 10 nanofarad, and 147 nanofarad ceramic capacitor. Then we have also used 100 nanofarad ceramic capacitor. Then coming on to the next capacitor, it's not ceramic but it is electrolytic, and that's of 100 microfarad. Then we have used a 30 meter winding wire of 0.25 mm diameter. Then we have used a diode 1N4148 signal diode. Then we have used a 5.6 voltage Zener diode, a 3 mm red LED. Now coming on to the next part, which is the active components or the important or the main elements of a project, that are the transistors. So we have the BC 547, 557 and 338 NPN and PNP respectively, the transistors. So we have in total of 5 transistors. Then we have a 1.8 ohm mini speaker, which shows our output. Then we have a 9 volt battery, and then we have a soldering wire of 47. So coming on to a circuit diagram now. It basically shows the schematic of our whole project and how all the components are connected to each other. So we have our Zener diode, then the two coils of 70 Tesla and 50 Tesla respectively, then connected accordingly to the transistors and the capacitors and the resistors. And on the output side, we have our 8 ohm speaker, which is connected to our BC338 transistor, and then an LED which basically showcases the state of the metal detection on or off, and then we have a voltage source with the switch. This same diagram we have simulated on Proteus design. Over here one change is made, that we have added a CRO so that we can see the graph and the plot of the output, or how is the wave being generated. The rest of the circuit is same, whereas L2 and L1 have values of 3.62 Henry and 2.53 Henry. Then we are making a PCB design layout on using EagleCAD software. So basically this is how a PCB is going to look. So thank you so much. Now we will move on to the working of the circuit, and that would be explained by my fellow colleagues Aryan and Shubham. Thank you.
So now we start with our circuit. The first block is a feedback oscillator consisting of the first transistor Q pi, the capacitor C pi, the inductor L2 and the inductor L1. The first transistor is turned on via the diode in the emitter of the second transistor, Q4. This diode receives its turn-on bias from the 1K8 resistor. The resistance of the receiving coil is very small, and the base of the first transistor sees a turn-on voltage from the voltage across the diode. The variable resistor in the emitter starts at a low value for our description of the circuit. The first transistor has a high gain at this point in time, and the transmitting coil forms a tuned circuit with a frequency of approximately 15 kHz, and a small amount of noise is always present in any circuit and causes a small waveform to be produced by the coil and the capacitor. This waveform is passed to the receiving coil through the air, and a small amount of voltage is produced across it. Since the end of the receiving coil connected to the diode, it is fixed and rigid, and the signal produced by the coil is passed to the base of both transistors. The coil is connected, so the voltage it produces turns the first transistor on harder, and thus the waveform produced by the tuned circuit is increased. Since the resistance of the pot is minimum, the amplitude of the waveform will be a maximum, and this will have the effect of turning on the second transistor, so the voltage on the collector will be very low. The signal on the collector will be a waveform, but this is smoothed by the C4 capacitor. As the resistance of the pot is increased, the voltage on the emitter will increase and the base to emitter voltage will be less, so the transistor will not be turned on as much. The waveform produced by the tuned circuit will reduce. This will be reflected in the receiving coil, and the second transistor will also get turned off slightly. The voltage on the collector will rise, and this will be passed to the second built-in block. When a metal object is placed in the center of the coil, some of the flux enters the object and causes eddy currents in it, and this flux is lost. The receiving coil does not get the full amplitude of flux, and the transistor is turned off a small amount. This increases the voltage on the collector of the second transistor and is a tone to be produced by the next three transistors. Now we come to the second block, the voltage controlled oscillator. The voltage controlled oscillator is a simple, direct coupled high gain amplifier with a 10N feedback capacitor to produce oscillation. When a voltage appears on the base of the third transistor, it turns on, and this turns the PNP transistor. The voltage on the collector of the PNP transistor arises, and this pulls one end of the 10N capacitor via 1 kΩ resistor towards the positive rail. The other end of the capacitor is connected to the base of the third transistor. This turns on the third transistor. They keep turning on until both are fully turned on. This happens very quickly, and during this time, the 10N capacitor starts to charge. Current flows through the base emitter junction of the third transistor. As the capacitor charges, it develops a voltage across it. This causes the charging current to reduce. The third transistor gradually turns off, and this turns the fourth transistor off slightly. The voltage on the collector of the fourth transistor drops, and the voltage across the 10N capacitor causes the third transistors to turn off completely. This turns off the fourth transistor, and now both are fully turned off. The 10N discharges through the 56K, and the cycle repeats. The capacitor takes a very short time to charge and a longer time to discharge. This is why the output consists of a very short spikes. Now we come to the reason why the frequency alters. As the voltage from the previous building blocks rises, the charge time for the first 10N capacitor is less, and thus the first transistor in the oscillator circuit is turned on in a shorter period of time. This capacitor is discharged when the two transistors are turned off, and to lead the second 10N is taken to the near 0 volt rail by the 1K resistor in series with another 1K resistor and the base of the driver transistor. It is fairly complex, and you have a CRO. You will notice the waveform on the 10N capacitor go below the 0 volt rail. This is how the two transistor direct coupled amplifier turns into a variable frequency oscillator.
The output of the oscillator is connected to a driver transistor via a 1 kilo ohm resistor. The resistor prevents high currents flowing when both transistors are turned on. The driver transistor is directly connected to an 8 ohm speaker. The 18 ohm resistor reduces the volume and prevents large spikes appearing on the power rails. The result is a clicking sound. Running the simulation, we can clearly hear the clicking sound and also see its graph. Here, the graph shows a sine wave oscillation, and it is a bit spiky at the top because it is a real graph and not an ideal graph. The driver transistor amplifies the VCO's output to create an amplitude signal that indicates the presence of a metal. How it works: a driver transistor connects the VCO to an 8 ohm speaker. The speaker produces a clicking or beeping sound depending on the frequency from the VCO output. An 18 ohm resistor smoothens out the large spikes and reduces excessive volume. Some things that should be kept in mind are: voltage stability is critical as fluctuations affect the circuit sensitivity and stability. And also, a Zener diode is temperature sensitive, and changes in the temperature in the diode may still cause gradual frequency drift. The above described metal detector has a wide range of real world applications. Here are some: security screening. Metal detectors are widely used in airports, courthouses, etc. to prevent weapons and unauthorized metallic objects from entering. They help detecting items like knives, guns, and other weapons concealed on a person and their belongings. Archaeological exploration. Metal detectors assist archaeologists in finding buried artifacts, coins, and other historical items in fields, beaches, and historical sites. They are particularly valuable for locating small metallic artifacts that might otherwise go undetected. Construction and utility work. In construction, metal detectors are used to locate metal pipes, revas, or buried cables before digging or drilling. This helps to avoid accidental strikes that could lead to costly damages. Environmental cleanup. Metal detectors aid in environmental cleanups by locating and removing metal debris from parks, beaches, and forests. This helps maintain safe and clean public spaces and protects wildlife from injuries caused by discarded metal objects. Food industry safety. Metal detectors are widely used in food processing to detect any metal fragments that may have accidentally entered products. This ensures food safety, helps maintain quality control, and prevents costly recalls due to contaminations. Medicine and health. In hospitals, handheld metal detectors can help locate metal fragments in cases of gunshot or shrapnel injuries. Additionally, certain medical devices may include metal detecting components to ensure patient safety during surgeries and procedures. Each application leverages the fundamental principle of metal detection, but may involve specific adjustments in sensitivity and design to cater to its unique requirements. Thank you.